Alright, today we're going to look at limits, when we can find limits by direct substitution. Before we do that though, I do want to take a moment to look at the homework, and specifically these ones with the graphs, okay? However, before we get to that, were there any questions about the limits that you found with the tables?
Can you post that on the website? Like
The what?
Did you record it yesterday?
Yes, I did. It's up.
We're supposed to do it with calculator, right?
Yeah. Oh yeah. So, okay. Now let's look at the ones with the graph. Some of these are pretty easy. Okay. You'll notice because this graph is continuous here, as x approaches -4, which is right here, we're going to approach from the left, it's coming down and it's approaching a particular value. As x approaches from the right hand side, the value of our function is approaching from below, alright, but it's approaching that same value. And in this case, because it's continuous, you actually can just plug in -4 and you get 16 minus 3 is 13. Okay? That one wasn't real easy to tell just because the graph, they use such a big scale for their graph, it was hard to tell exactly what point you were approaching. Alright? Well, let's just run through some of these and get some answers. On number 30, as x approaches 2, which is that point where it's undefined, what would the limit be? What's the value of our function approaching as x gets closer to 2? 12. Okay? So the limit, even though it's undefined at that point to 12, okay, the limit, remember, is what we are approaching. That's the key. So the limit would equal 12. Alright? Next, with 31, as we approach this value of -2, what's our left-hand limit? -1, okay. We're approaching -2 from the left-hand side, and the value of f of x is actually constant there, so it's still approaching -1, okay. What are we approaching from the right-hand side? 1. So what's the limit?
It's undefined.
It's undefined. The limit does not exist, okay, because the left and right-hand limits are not equal. Alright? How about number 32? As we approach 1, where this asymptote is, what would be our limit?
Again, it doesn't exist.
Again, it doesn't exist. This is one of those cases where, as you look at the left and right hand limits, you could have one of two answers. You could either say the left hand limit is approaching -infinity, or you could say it does not exist. Your book is going to say it does not exist. Okay?
But mine is 31 not exist
Because you're approaching different values from either side.
okay.
Okay? And here, regardless of whether you say it doesn't exist or approaches -infinity, and as you come from the right, whether you say it does not exist or approaches +infinity, either way, they're not approaching the same value. So we would say the limit does not exist. Okay? Now, these last few, well actually, let's look at the last two and then we'll come back here to 33 and 34. They present kind of an interesting dilemma for us. We have the limit as x approaches pi/2, so this asymptote right here, of tangent of x. So what's our left-hand limit? +infinity. What's the right-hand limit? -infinity, so our limit is? Yeah, it does not exist. Okay?
Why?
Because again, here we're approaching positive infinity on the left-hand side. We're approaching negative infinity on the right-hand side. They're not approaching the same value.
If there's
So
a,
it does not
if
exist.
there's an asymptote, pretty much there's no limit.
Theoretically, yeah, you could put, anytime there's an asymptote, you could say does not exist because, remember we said even if your asymptote is like this, and it's going up on both sides,
It's never gonna be-
you could say it doesn't exist, or you could say it's positive infinity,
Yeah.
but doesn't exist will work as well. Let me just real quickly here. So her, him. Okay. Alright, secant is the same way. Alright, we're approaching positive infinity from the left, negative infinity from the right. So we get does not exist. Alright?
So if you ever have an asymptote, it's always going to be does not exist.
Yeah.
Okay.
And like I just showed, it could possibly be positive infinity or negative infinity, but a valid answer for those is doesn't exist as well. So now 33 and 34 presents us with a little bit of a dilemma. Okay, we looked at one like 33 yesterday. What did we call this kind of behavior?
Oscillating?
Yeah, this is oscillating behavior. We're going between -2 and +2. Okay?
Yeah, between two fixed values.
So this one, it does not exist. Okay? The reason is, no matter how close you get to 0, it continues to have that bounce back and forth. I could make this x, a 0.00000001, and I'm still going to get it bouncing back and forth between -2 and +2. Okay? What is the limit here of the sine of pi x over 2 as x approaches -1?
Negative 1.
Okay? What do you guys think?
Negative 1.
Right. So you're saying it equals -1.
Or that might be one of those left and right hand limits where they're different.
No, there is a
Okay?
Negative 1 and 1.
so it keeps going up.
So, if that's the case, it doesn't exist. Here's the question on this one. Is this oscillating behavior?
No.
Well, actually,
Well,
no.
not in what we can see.
I think.
I mean, technically it is, but like at the scale we see, it's not.
Okay? Well, tell me what you think, alright? Others get involved here.
Well, can we assume that it continues in the same pattern? As
Well, is there a limitation on our domain?
No. Okay, so it's gonna be.
No, so yeah, it would continue like this and like this, okay?
So it's
Yeah,
like
so
negative
So
one.
then it does
It's
not.
only up to
exist.
-1, so it's.
Yeah,
Yeah,
negative
so
one.
the limit, wouldn't the limit be 1 to
Yeah.
-1?
Yeah.
But it's the same thing as the other
Okay.
one, just that it's more spaced out.
Yeah, that's what I'm.
Yeah,
Yeah,
there's
Okay.
but the one that's more spaced out, but it doesn't, like it
It's
gets.
just because we see it at a different scale.
Where would we draw
No,
the
but
line?
the
Exactly.
other, doesn't it like open up at the end? So
Yeah,
isn't that
that's-
changing? No, it's just the way it's
No,
drawn.
Well, it does keep going. Here's the thing, how many of you would say that this is probably -1?
the limit.
The limit is -1, okay? How many of you would say this qualifies as oscillating behavior, so the limit would not exist? Okay? Alright, so how about the 3 of you who didn't vote? Okay? Well, what do you think?
-1.
Well, you voted. What do you think, guys?
Josh, what do you think? -1 or does
Negative
not?
1 or no?
Wait, what's the question? I got this.
Is this oscillating behavior?
Is it negative
Or
1 or
does our limit, I mean, it sure looks like it goes to -1 at both sides, right?
I'm gonna go with no.
So you're saying there's no limit?
It wasn't a yes or no question.
It's not a choice, or it's not a.
Negative
No
1.
limit.
No limit, okay.
You traitor.
Let's look at this a little closer, and let's really make sure we understand what oscillating behavior means, okay? oscillating behavior is not the same as periodic behavior. Okay? And I like this problem because it really forces us to define this very carefully. Yes, the sine function does go between -1 and +1, but that is not the same as the oscillating behavior. And really kind of the key here is that you have this pi over x. So for one thing, the value you're approaching, it's not defined at. And as we said, if we zoomed in here really, really close, we would see it continue, the closer and closer we got to 0, it would continue to go back and forth and back and forth. And if we zoomed in even more, it would continue to go back and forth, back and forth. Alright, you've got that oscillating behavior, it's going back and forth no matter how closely you zoom in to look at it. So even though this one, the scale is, it's a little more spread out, that's not why this is not oscillating behavior. This is not oscillating behavior because as we approach it, it doesn't continue to jump up and down. It is approaching an actual value. Okay? Part of that has to do with the fact that yes, the function is defined at -1, okay? But it also has to do with the fact that, no matter how closely we zoom in on this point right here, it's not going to suddenly jump back up to, up to 1 as we get closer. Okay? Does that make sense? Kind of? Alright.
But notice
So-
that when x is in the, what is it called? Under?
Denominator?
When it's in the denominator, yeah, it's mostly undefined.
That's one way, to tell. Because here's the thing.
1 over x
If
squared.
we treated this as oscillating behavior and said the limit didn't exist, then we would never be able to find the limit of any of our sine or cosine functions. Because they all oscillate between +1, -1, or whatever the amplitude is. Okay? So, that's an important distinction to make. And actually, this is a case where we actually could simply plug in -1 for x, and then sine of -pi/2 is -1.
Why is the limit -1 enough? Oh, never mind.
Because, we're approaching -1 down here. Okay? So, with that kind of leading into this, I said in this case we are able to actually plug in our value. Okay? So, when else are we able to find a limit by direct substitution, by simply plugging in that value x is approaching? Okay? When else can we do this? I'm going to give you a couple of specifics and then kind of give you a general rule for it. Okay? One case is when you have polynomial functions. Alright, if you don't have a denominator, you're just dealing with a regular polynomial, you can just plug it in, because polynomial functions are defined for all real numbers. Okay? That's part of what makes them a polynomial function, is they're defined for all real numbers. Okay? Another case is a radical function as long as you are not approaching the endpoint. So for example, if we had the square root of x plus or x minus 3, okay? If we were finding the limit of the square root of x minus 3, as long as x was not approaching 3, you could just evaluate it, okay? Because, there is no left-hand limit at 3, so the limit as x approaches 3 would be undefined. But if we were approaching, say, 12, okay? It's just somewhere over here, here's 12. So what is that function approaching, okay? And we could simply plug that in. 12 minus 3 is 9, the square root of 9 is 3. So our limit would equal 3.
So
Okay?
the answer should approaching to 3.
What?
So the answer for this one is approaching to 3.
Yes, the limit as x approaches 12 of the square root of x minus 3 would equal 3. Yes?
So there can be different limits depending on which point you pick on the graph.
Yes, because x is approaching a different value. Your function, unless it's a constant function, your function is going to have different values and be approaching different values at different x values. Okay? Another case is when we have exponential functions. Okay? Exponential functions. I'll erase this here. If we have the limit of e to the x, okay? The limit as x approaches 0, let's say, of e to the x. Alright? Here's our graph of e to the x. Notice as x approaches 0 from either side, it's approaching that point. Does anyone know what that point would be?
1.
1. Okay, 0, 1.
Maybe.
So if I just plug in 0, e to the 0 is 1. Okay?
What the radical function?
All right.
Is the same.
A radical one is the one we just did with the square root. Here the exponential function, we have e to a power. Okay? And by the way, that works for 2 to the x or 5 to the x or anything to the x power. A general rule, though, is this. Any function that is continuous around the value that x is approaching, you can find the limit by simply evaluating the function at that point. Okay? Let me explain what I mean. If I have a function here, it doesn't matter what's going on anywhere else. We could have, something like this. We've got a hole here and an asymptote here and all that. None of that matters if we want the limit as x is approaching, this value over here. Because at this point over here, this hole is having no influence on us. And this asymptote has no influence on the function. We are simply looking at that part of the graph, and because our function is continuous around that part, I can find the limit by simply plugging that value of x in. Okay? Yes?
So if you try to find the limit of the x where the asymptote is, you can't. It's not doable, right?
Yeah, here, as we approach this value of x, the limit would not exist. As we approach this value of x, if we tried to plug it in, we'd end up with something that's undefined. So we would need some other strategy to find out what that value is. We could use the table to approximate it. We'll actually learn a better way next week. Okay? But if we're approaching a point that isn't involved in a hole or an asymptote, and isn't an endpoint like with our radical, we can just plug it in. Okay? So let's look at a couple of rules that would kind of govern some of these. We've got a number of different rules, but as we go through them, you'll notice a lot of them are just kind of make sense as we work our way through them. So first of all, these are what are known as limit theorems, or you could say properties. Properties is maybe a better term simply because they do just make sense if you think about it. Okay, so we don't necessarily have to prove them all mathematically because they make sense. But anyways, the limit of a polynomial I already mentioned, but just so you can see kind of the notation here, the limit as x approaches c of f of x, if x is a polynomial, is f of c. You're simply evaluating the function at that point. Okay? Another one that's kind of obvious like this, but is the limit of a constant function. If y always equals 5, then as you approach x equal 2, what is our function going to approach? 5. Okay, it's not changing, so it's approaching the same value all the time. So in this case, it doesn't matter what you approach, it's still going to be that constant. So here we have a function equaling some value of b. So if we take the limit as x approaches anything of that constant, it's going to stay that constant. Then we have a constant multiple. Okay? The limit of a constant multiple. Here we have this function, but we're multiplying it by a constant. And what we can do here is if we're trying to find the limit of that, we can take that constant outside of the limit. Okay? So let's say, you have, this is your f of x right here. And let's say this is some constant times f of x. Okay? If I picked some random number, actually let me use b to be consistent here. If I picked some point here at c, that would be the point c f of c, right?
Yeah.
Now, the point on this graph would also have c,
And then BF of C.
but it would be, b times f of c. And you can see here that because we have this if we're taking this limit, as we approach from the left, we're approaching this value. As we come from the right, we're approaching that value. That's f of c. If we just multiplied that by the constant b, we'll get the same thing as if we approached from the left and right on the constant multiple. All right? So basically what you're able to do is take the limit of the function, pull the constant out of it, and just multiply by that at the end. Okay, which can make evaluating some of these easier. Okay? Alright, now another case. We have the limit of a sum. Okay? The limit of a sum equals the sum of the limits. Alright, so here we have a function that is made up of 3 separate functions added together. Okay? So, we could rewrite this as the limit as x approaches 5 of x squared plus the limit as x approaches 5 of 3x, and then if I have 3x, what could I do with the 3?
Put it up.
I could pull it out, yeah. So 3 times the limit of x, and then I could have a plus the limit as x approaches 5 of the square root of x over square root of x minus 1. So here's the thing, these are 2 real easy limits to find. Okay, the limit of the x squared would equal 25, and 3 times the limit of x would equal 15. So now, we don't have to worry about that aspect of the problem anymore. We can just focus in on this more complicated aspect. Okay? Now, question, where is the asymptote on this function, square root of x over square root of x minus 1? It's at 1. Okay? So, are we approaching anywhere where it's not continuous? No. So how could we evaluate our limit? Just plug it in. Yeah, we can just plug it in. So square root of 5 over the square root of 5 minus 1.
Or we can directly plug it.
We can directly plug it in because the only place where this is not defined is when x does not equal, is when x equals 1. Since we're approaching 5, it's continuous over at 5.
Where are we getting the 5 from?
That's just part of the problem. The problem was take the limit as x approaches 5.
Oh, okay.
So,
The last function x cannot equal to negative, right?
yes, x could not be a negative either. So if we were, and in fact, if we were approaching, say, -3, even though these two parts would exist, if we were approaching -3, this would be undefined. So the entire thing would have a limit that was undefined.
Like we also can type all things in the calculator.
Potentially, yeah, you could. So. Alright, here's another one. We have the limit of a sum, now the limit of a product. Okay? And this works no matter how many functions are involved. The limit of a product is the product of the limits. Okay? So, I could rewrite this as the limit as x approaches 5 of this first function, x squared plus 2, times the limit as x approaches 5 of the second function, x minus 7. Okay? And I know I'm dealing with some pretty simple functions. You might say, well, I could have just FOILed that together. And that's true. But this applies for all types of functions. If you can find the limit of each separate part, then you can multiply those limits together. So here the limit of this first part is what? 27. The limit of the second part is -2. So we have a -54. Okay? Okay? So, we have the limit of a sum, we have the limit of a product. Yes?
But we can for this one we can directly plug a portion number into the equation.
Yeah, we're plugging that 5 directly in, because those are polynomials. Okay. Now, we have the limit of a power. Here we're raising a function to a power. Okay? The limit of a power is the limit of the function raised to that power. Okay? So here we have some function raised to a power n, and then we're taking the limit of that. What we can do is just take the limit of the function itself and raise that to the power of n. Okay? So here, this is cubed. We have x squared minus 21 cubed. I can rewrite that as the limit as x approaches 5 of x squared minus 21. Okay? And then after I find that whole limit, I can cube it. Alright, so now we're back to one of our rules that we already know. We're finding the limit of a polynomial. Oh, forgot that. What is the limit of x squared minus 21? 25 minus 21 would be 4, and then I do the 4 cubed. Okay? I do the 4 cubed, and that would be the 64. Okay? But again, notice how it keeps our number smaller, and it also keeps us from having to expand this out. Okay? Because if this were not true, we would have to multiply that out. And then evaluate that polynomial. So, again, we have sums, products, powers, now quotients, okay, for the limit of a rational function. A rational function. This is one where you do have to be careful, because there's one caveat here that we have to take into account. Alright? The limit of a quotient, or a rational function, is the quotient of the limits. So the limit as x approaches 3 of x squared plus 2x minus 5 over the limit as x approaches 3 of x plus 2. Okay? This will work so long as the denominator does not equal 0.
So if
Okay.
x approaching -2, so there's no answer.
Well, if x approaches -2, we need a different strategy. Okay? We would have to use a different strategy, which we'll look at those situations next week. Okay? Now, in this case though, this is not equal to -2, or we're not approaching -2, so this is not going to equal 0. In fact, our denominator is 5. Our numerator, there's a polynomial, and we can evaluate a limit of a polynomial by simply plugging in 3. What would we get there?
10.
10, okay. 9 plus 6 is 15, minus 5 is 10. So the limit of that whole thing equals 2. Okay,
It's not that bad.
not that bad.
Is it the last one or is it?
Okay. Well, what I do want to do is preview one of the kind where it does end up equaling 0. And I'll just show you how we can do this. But we'll spend time actually practicing it next week. If I asked you to factor x squared minus 36, how would you factor that?
X plus 6,
X plus 6, x minus 6, okay? What if I asked you to factor x squared minus 5, using the same concept?
X plus square root of 5, x minus square root of 5.
Yeah, x plus root 5, x minus root 5. You're using the difference of squares. And back in Algebra 1 when you first learned it, your teacher always said these had to be perfect squares. And in Algebra 1 they did, okay? Now though, we can take that same concept and expand it. In fact, I don't even have to have a difference. I can do it as x squared plus 5 as long as I see it as x squared minus a negative 5. Right? Okay. If I have x squared minus a negative 5, what's the square root of negative 5?
Oh, square root of
There's not.
Square root of negative 5?
Oh, you want the actual number?
Undefined.
Square root.
We know how to do square roots of negatives.
I.
Root 5, right? I root 5, I root 5. Now, when we're doing limits have to be real numbers. So if we got something like this,
It would be, no, it's not.
we wouldn't mess with it. But let's use this principle here to help us evaluate this limit. Because if we plugged in 36, we would get 0 over 0, which is known as an indeterminate form. Okay? However, how could I rewrite my numerator?
X minus 6 x plus 6. Oh no, sorry, I lied.
Two seconds.
What would it be? Plus 6 minus 6, but what would it be? Plus 6 and minus 6. The square root of x. Alright? So check this out. Our denominator is square root of x minus 6, and that allows us to reduce. And then look, we're back to something that is continuous around the value 36, so we can just plug it in,
Of course.
okay? So we plug it in now, and it's just the square root of 36 plus 6, which equals 12. Okay?
World shortcuts.
We'll handle that more next week, okay?
So you wouldn't want us to write that down now, it's just like a little,
You can. This is just a preview of what we're doing next week. So, but for now though, I do give you some. These are ones where they're using f of x and g of x just as general functions. And they're asking you to do, if we're finding the limit of -2 times g of x, use those rules that we looked at earlier to evaluate it if we know that the limit of g of x is 6. Okay? Then there are a couple others here. You're limiting by direct substitution, or you're finding the limit, not limiting. You're finding the limit by direct substitution, but in some different contexts. Okay, so just some practice with those. Okay? Any questions?
oh,
Yes.
I'm bathroom.
Alright.
Yeah.
Okay.
You probably have to go with limits.